But what we are going to do before we do that is we're going to do another type of calorimetry problem known as bomb calorimetry. And it actually is, I think, significantly easier to figure out.
Mr. Mayor,
Yes, sir.
may I go to my locker?
Yep. So I kind of showed you. Let's turn your books to 245. I'm going to just show you the difference between a bomb calorimeter and a regular calorimeter. I know the regular calorimeter on 245 is pretty like makeshift. Like it's just like you could make one out of styrofoam cups. But that's just, in essence what a bomb or what a regular calorimeter would look like. Just some insulated object, you put water in it, and you study what happens to a chemical reaction by figuring out what happens to the water, essentially. Okay, so if you flip a couple pages to 249, okay? In 249, you've got another calorimeter. This one's called a bomb calorimeter. Now, what's really the difference? Well, here's really the difference. In a bomb calorimeter, it's done in a contraption that keeps the volume constant. So if you kind of look there, it's in an enclosed in chamber. I think it's called a steel bomb. You see it as you look on the description on the left. It's got that like chamber there. Obviously, it's not broken half like it shows, but it needs to be like that to show you what's going on. Okay. Well, the volume is not going to be able to change in that particular closed chamber. And so if that's the case, you can study energy changes under a constant volume, which if you remember, we had an equation for energy. Okay, our internal energy. If we know that there's constant volume, that's going to take away one of these variables in that equation. What will that take away? If I'm under constant volume, what is that going to take away? What variable? Yeah, why? Okay, if the volume is not changing, we can assume no work is done. So none of the internal energy is coming from work. It's all coming from what? Heat. Okay? So if that's the case, if we're under constant volume, we can say our internal energy is really just what the heat energy either was transferred to or from the system. Okay, so that's the significance or the real usefulness of a bomb calorimeter. I also think that it makes it considerably easier, and I'll show you why. So now you could say QV. What do you think that means? What does QV mean?
It's under constant volume.
Under constant volume, because I said change in H would be QP, which we said was under constant pressure. All right. So let's do a couple bomb calorimeter problems. First one here. It is a different equation. It's a little bit easier equation. Here it is. QC change in T. What is C?
Celsius?
No. That would be G. Never mind.
Capacity?
Yeah. I don't know why I put SB in the answer, but this is just your heat capacity. And that unit was just a joule per degree C. That was the one that didn't have what involved with it? Per what? Gram. So there's no per gram, no per mole. It's just how much energy needed to raise 1 degree C. Well, if you're under constant volume, you don't really need to worry about the amount of grams you have in it. Now, let's look under this situation. We've got a certain sample of octane that's placed in a bomb calorimeter. Right? We know the heat capacity of the bomb calorimeter is this. So that chamber that is enclosed has a heat capacity of that. So we can figure out how much energy was either taken or given to the bomb calorimeter by studying how the temperature changes the bomb calorimeter. What's happening to the temperature of the bomb calorimeter? Okay, so if you got a closed metal container, okay, and you do perform a reaction in that metal container, the energy that is either given off inside the container or absorbed into the container is going to come from the container itself. So the container is your surroundings, if that makes sense. Okay? As we're in the other situation, in the regular calorimetry problems, what was the surroundings? In a regular calorimetry problem? The water was. Okay? Essentially, the thing that was surrounding your reaction was the water. Here, it's an enclosed container, and that container has a specific heat capacity. It's that. All right, so let's figure out some stuff that we have. We know that our C is 11.3 kilojoules per degree C. What else do we know in this particular situation?
When the change in temperature is positive 2.25.
What does that tell you about this reaction? Yep. Anything else that is important? I guess we have a mass, which we will need because it wants us in kilojoules per mole. We can figure out kilojoules. Oh, one thing to note too. C is in kilojoules, as where CSP is usually in what? Joules. Okay, so just make a little side note about that. That's pretty important to remember those units. Okay, so as you can tell, we can find Q pretty easily. Yep. Just plug and chug, correct?
Yeah.
Once we have Q, we can take and divide that by moles after we do what with this?
Where's that from?
Okay, why don't you guys solve now? Find your Q, find your number of moles, and divide.
What's octane? Should get molar mass.
Okay, check it out.
Oh dear, it's long. C8H18. Alright. That's one of them, there's two of them. There's also CH36, CH3. That's not helpful.
C818.
I'm guessing C8H18. It's a hydrocarbon. Yeah, C8H18.
Oh.
Yep.
Is it C8H18?
Oh, you don't know the
Octane? No.
formula for octane.
No.
Sorry.
Is it C?
Probably should give that to you. It's C8H18.
I go C.
I'll just give you the molar mass here. It's 114.26. Sorry, guys. I think that would be up there. You guys probably just did, hey Siri, what's the formula?
I did that.
Did it give you
Yeah.
C8H?
Well, it also gave me like H36.
I'm guessing that's just the
It's the other one.
non-empirical formula version?
Yeah.
Yes. Don't do that. Never put your water there. says in kilojoules per mole.
So it's already in kilojoules.
Yes.
So we're good.
We gotta divide by moles.
Yeah. But
Yep.
already converted to joules.
No. What you guys get in kilojoules per mole? 5,550 or like,
I think 55,000.
alright, it could be just how we rounded. So I have negative 5.55 times 10 to the third kilojoules per mole. Now why did I put a negative on that? Okay, because we know that the bomb calorimeter gained a positive amount, 25.4, right? So then the reaction had to have given off that much, therefore it had to be negative. Okay, also says release up there.
I was like, what? How do you think it?
Well, you should always remember, this is the equation for the bomb calorimeter. We don't have a separate equation for the system. If we could just come up with an equation to figure out all this stuff from the system's perspective, that would be awesome. But it's much more difficult. So we use bomb calorimeters to really figure out what's happening in a reaction by figuring out what is happening to the surroundings around that reaction. All right. All right. Here's what we'll do. I'm already taking my phase.
Oh, that's like a long.
Well, the homework took us a while to get to do. That's really the main reason. Well, now I might look into it. Okay. Okay, so essentially in a nutshell, this is saying hydrogen is a possible substitute for natural gas. Let's try to figure out per gram what gives off more energy, hydrogen gas or natural gas. What was that? So we'll essentially have to do two different bomb calorimeter problems. So our Q equals C change in T. We'll say this is for CH4. And then we'll do another one for H2. Now they're both done in a bomb calorimeter, which has a heat capacity of this. Makes sense? Now it's not being done at the same time, guys. Just don't mess that up. So I'm just going to plug both those in now. All right, let's look up at what they say is the temperature change for these guys. When methane gas is burned, the calorimeter increases by 7.3. And when hydrogen gas is burned, the temperature increases 14.3. Okay, if we take and plug that into our calculators, we should get 83 kilojoules for the first guy. And I'm going to put a negative on that. Why? Because it's going to be released. Okay, the other one should be 162. And I'm also going to put a negative on that. And we need to take those two numbers and divide them by the what? To finish this. Compare the energy of combustion per what? So this is pretty easy. We got 1.5 gram sample of methane gas. And we got a 1.15 gram sample of hydrogen gas. I know this probably looks like way harder of a problem based on the fact that there was so much information they threw at us. I wrote the per gram differently in the two. So it's the same thing. Ah!
Kilogram per measure.
There we go. There's your theoretical Jolly Rancher. Alright, we got 7 minutes to do Hess's Law.
What do you compare?
How do you compare it? You would just say, looks like the amount of energy H2, what?
That's what you write? Looks like.
Well, no, I would say the energy given off per gram of hydrogen is about 3 times as much as the energy given off per gram of methane. Now, we're going to talk later in a different section, why don't we use hydrogen as a fuel source? It appears to be way better per gram. We're going to talk about that near the end of the chapter. Okay? All right. Woo, Hess's Law, my favorite. Lock it in, baby.
No.
Since we should have this pretty much down, and you'll remember it pretty easily once I start going over it. Here's the situation with this, okay? Because enthalpy is a state function, remind me again what a state function is. It's half independent. Okay, final minus initial. Okay, we can be totally not care about the path that a particular reaction takes from an enthalpy standpoint. So what Mr. Hess came up with is he said if you know the enthalpies of each individual reaction, you could add all those together if you can get those reactions to cancel things out to get a desired unknown enthalpy of an unknown reaction. Just like you would do in a math problem or a math class. However, there are 2 really important rules. Okay? It says if the coefficients of an equation are multiplied by a factor, the enthalpy must be also multiplied by the same factor. That makes sense. If I have twice as much stuff, I'm going to have twice as much enthalpy. If I have 3 times as much stuff, I'm going to have 3 times as much enthalpy, correct? That makes sense.
Yeah.
Second thing, if you reverse an equation, which these are 2 things we're going to have to do to solve this. If you reverse an equation, the sign of change in H must change. Why would flipping an equation make the sign of enthalpy change? Yeah, right? If it's exothermic one direction and you go the opposite direction, it's going to be what? Endo, okay? Now, for solving these problems, what we need to do is be able to flip equations and balance coefficients so that we can cancel out like terms and get to our desired outcome. You should remember this from a couple years ago. We'll start with a really easy one, and I didn't write the whole darn thing out here.
Not here.
The next one. Why don't we do the hard one? We'll stick away from the easy one. Let's do this one. Okay? So if you remember in Hess's Law, what they do is they give you the overall outcome, like the equation. But they do not know the change in H of that. But what they do is they give you the reaction mechanism, or what would also be known as the steps that are needed to get to your overall outcome. Okay? So what we need to do is manipulate these equations in a way that they would cancel each other out if they were on opposite sides, or they would add if they were on the same side, like in math. If you have 2 x's on the same side, what do? They add. But if you have 1 x on one side and 1 x on the other side, they would what? Cancel out. Okay? Same thing here. And it would make sense that if a reactant produces a product and then the next step, the next reaction uses up that product, it's bye-bye, right?
Yeah.
Okay. So here's what we do. Now, I'm going to actually take this equation and match up the arrows because it's just easier to see. I didn't change the fact that this is still a positive 44 kilojoules, okay? So what we need to do is we always look at our final equation. We need to get this to add up or cancel out so that I only have these guys. So let's look at that first. If you recall, you're going to look up here and figure out where is B located.
Very first one.
Very first one, but it's only in the very first one, right? That's good news for us. Okay? There are two questions we should ask. Is it on the correct side of the equation to match up with what our final answer would be? And does it have the correct coefficient to match up with what our final answer should be? The answer for both is a resounding yes. So if you remember, we lock it in, baby! Remember that? Okay. Yep.
I never did it when we did it.
Yeah, because you guys are too cool.
I just did it really fast and got the answer.
Okay? Once we have locked that in, I can't change this equation, manipulate it, do anything to it, because if I do, it puts this out of place and potentially the wrong coefficient. Make sense? Move on to the next one. H2. Where does H2 appear? Third one, and only in the third one, right? That's good news. However, something's wrong with it. Doesn't have the right coefficient, but it is on the correct side. So I'm going to take and multiply by 3 to get the correct coefficient. Well, in math, when you can multiply an equation by a factor, but you have to do it to everything, otherwise it's no longer the same equation, correct? So this would be A3. This would be 3 over 2. That would be A3. And since we have 3 times the amount of stuff, I'm going to have to multiply the amplitude by 3 and then lock it in, baby. Okay? Next, now that I've got that locked in and that locked in, let's keep moving on. B2H6, where does that guy appear?
The second one.
Second one, and only the second one. If it appears in more than one, maybe come back to it. Okay? What's wrong with that?
Somewhere on the side.
The wrong side, so we can flip it.
Change the sign.
I would always change the sign first before you flip it, because even me, I sometimes forget to go back and change the sign. It's really important that I put that that H2O is a gas there, because, so which one are we doing here? We're doing the second one. This needs to be a positive 2,000. Okay, flipping it. Yeah? Is that right? Okay, then we what? Lock it in, baby. I'm going to get rid of this. Now, everything should be in the right spot. Unfortunately, our waters aren't probably going to cancel out. So we have all the equations locked in except for this one. And if you look up here, do you see how the waters are not going to cancel out? Unless I do what? If I multiply this by 3, then my 3 as a gas will cancel, my 3 as a liquid will cancel. So now, finishing off. We should have everything that should cancel or should be left over. We have our 2B should be there, untouched. This should be untouched. And what was our last one, H2? That one should be untouched. Everything else should cancel out. Let's see. Okay, let's start with something easy. B2O3. Cancel. Here, here, opposite sides. Yeah? H2O is a gas, here, here. H2O is a liquid, here, here. Then we've got O2 is the only guy left. Alright, we've got O2 there and O2 there on the same side. If you add those, what does that become? 3, right? 6 over 2 would be 3. Would that cancel out with that 3? this and this added together would cancel out with that 3, leaving us with our only 3 that are remaining on the correct sides with the correct coefficients. The final answer would then be add all of those steps together. Plus 3 times 96. Plus 3 times 44. Plus a positive 2032. And that should give you 36 kilojoules. Wow. All those big numbers. That's your answer.
Can I try to keep?
Yeah.